Okay, so it's time, so let's start with the lesson. So today we're going to see object-oriented design. It's going to be a brief lecture, as usual, on this topic. So ideally, so if you ask me, if I have to start from scratch a C++ course, this will be probably the first lecture. So this is probably one of the reasons why we don't dive really deep into some topics, because for me it's also important that you can get on track with C++. But if I have to choose, I will actually expect from you that you know the first 5 or 6 lessons, and we can start from here, because this is basically the core ideas behind all C++ programs, and this is how the language evolved. Nowadays, it's not everything about object-oriented design, so the language evolved a lot, and actually now it's multi-paradigm, so you can use this, you can use generics programming, procedural programming, wherever you feel in the mood of using, but this is basically the foundation. So we're going to see like the most important things and ideas about object-oriented design with C++. As a disclaimer, 98% of these ideas are generic for any programming language. So actually, if you try to find books about object-oriented design, they don't focus on the language, because that's the implementation of the ideas. It's more on like how to work with these ideas. And also we are going to see 2 or 3 patterns today that they are not super cool or fancy, but I feel like you also need to see that you can use the ideas behind object-oriented design to make some patterns that you can reuse along your code. So let's first start with a really stupid example. So I wanted to actually rework this example, but I didn't have time, so we need to stick with this. So let's pretend for some reason you want to model some vehicles on your city, for whatever reason, right? And then typically you will start coding and trying to model this on separate models. So you will have, for example, a bus, a car, and a truck. The idea behind object-oriented design is usually to reuse code and to group objects that belong together in a class hierarchy, right? So, for example, in this case, we are going to design this with an object-oriented design in mind, saying we have a class vehicle, will be our base class, that this would somehow model all our vehicles in the city. And then for this class vehicle, we need 3 particular methods. So we have 3 capabilities for this class. One is going to be the fuel amount. The other one is going to be the capacity, like the number of seats that this particular vehicle has. And the other one is apply brakes. So these are all fake examples, and that's for the sake of trying to explain the concepts. So, and then we are going to have 3 other classes that will derive from this vehicle class, and each class will implement this functionality in a different way. But now we have some sort of relationship between these objects, because we know for sure that at least they all stick to the same interface. So let's try to see a really quick example on C versus C++. So let's open the inherited example. Yeah, let's open the editor. No, not here actually. So inheritance, and then we want to open this one. Okay. Why this is not? Maybe it's. Why is this not working? I have no idea. Come on. I can't open the folder. It's not that difficult, right? Okay, finally. So let's see the C example. So with C, you don't have this type of inheritance, right? So you don't have this way of expressing relationships between different classes. So you are forced to write a bunch of types and a bunch of functions that are related somehow, but they are not expressly related in the code. So in this case, so these examples, by the way, are on the web page. So there is a example zip file with all this code. So I encourage you to go and try the examples. So we'll have a type that we will call it vehicle, and this is how you define types in C. It's quite ugly. And then we will have like 3 sort of data members. And then we will have like 3 functions that will try to somehow pretend to be the getter function of this particular vehicle. And then we will have 2 or 3 derived types from this vehicle class. It's going to be a bus, for example, a car, and then that's basically it. But the thing is, you cannot express like explicit relationships between these types in C. And then you need to start to compose this type saying, okay, this bus, it's a vehicle, then you have a vehicle. And then if you see this example, you will see that it's quite complex to read and follow. Why? Because it's C. And then if we try to model the same behavior but with C++, we can get much better code and actually express these relationships between the classes. So we will have a class vehicle, this define a new type with some particular information. And then we can derive from this vehicle and implement the different type of functions for each type of vehicle within C++ with really small code. And then here I will explain what is the meaning of this right now, but here you're expressing explicit relationships between this type. Basically you're saying here a class, a car, is a type that is a vehicle, right? So it derives from vehicle. So it will inherit all the information from this class. So in order to make the lecture short, I will keep moving forward. But again, you should download these examples and try it on your place. So the idea behind inheritance, that is what I am trying to explain, is that a class and a struct can inherit data from functions from other classes, right? And this way we can express relationships between the types and also reuse code. There are basically 3 types of inheritance in C++. One is public, that is the one we use. That is like if you have a derived class from a base class and you say, I am doing public inheritance, you will basically, all the methods that are public will be public on the derived class, and on the protected one will be protected on the private, and so on. There are 2 other types of inheritance that we don't actually use, and it's not commonly used. So for now, let's stick to public inheritance. Public inheritance will keep all access to specifier or the best class. So what I said before. And this is basically how it looks on the syntax wise. So the idea behind this type of inheritance is that there is an is-a relationship. So a class derived inherits from publicly from a class base, and then we say that derived is a kind of base. And how we do it with this particular syntax. So when you express the relationship, you use the colon operator here, and then you say public, and then you specify the type that you're deriving from. So this allows derived to use all public and protected members of base, right? And derived still gets its own special function, so you can add more specification to this derived type, and then you can use your own constructor, destructors, and so on. So you don't actually need to, so you can augment the information within this class. This is a really dummy example, but it's worth to go through it. So basically, in this case, so first of all, let's see what we already know. So let's keep this aside. And then in this case, we will have a type that is called rectangle, and this type will have 2 members that is protected. And now it's this new keyword that is protected. So protected is the same as private. This means that if I create an object from this class, then I cannot access these data members. But classes who derive from this type will be able to access these members. If we mark this private, these 2 members, whenever I want to derive this type into a more specific one, like square for example, then I won't be able to access this to member. That's why we use protected. And then we have the width and the height for the rectangle. And then we have one constructor that takes as input the width and the height, and then it sets these two parameters. And then we have two getters methods, so the width and the height. So far, there's nothing new here. But what happens if we want to refine this concept of rectangle and say, okay, I can do better with some particular methods like square? Well, actually the width and the height are the same, right? And then that's where it comes this idea of inheritance. So you will create a new type called square, and then you will publicly inherit from rectangle. This means that you inherit all this information here because it's public and protected with the same access specifier, right? What you're going to change, for example, because you want to refine this concept, is the constructor. So if you pay attention to the constructor of the type square, this is the new constructor, you will only take one integer as input parameter, and then you will initialize the base class using the same parameter repeated, because the width and the height for a square is the same. And this is how you do inheritance, right? You want to refine a concept from a given class, and then you will add more specification. This is a dumb example. Again, try it. What we just did is something that we call function overriding. And this is one of the most common use mechanism to provide functionality across base class and derived class. So any function can be declared virtual. So the idea of overriding is that we have one. Actually, this is not overriding, but it's similar. The idea is that you have some function within the base class, and then when you derive, you change its functionality. In this case, we're changing the functionality of the constructor. So we are changing the prototype, so it takes different input of arguments and also how it works. So that's the idea behind overriding. So any function of any class can be declared virtual. So this is a keyword of the language, so you cannot use it for your purposes. The sun is killing me. So let's try to do like this. And then if a function is virtual in the base class, so in our example, the rectangle, then it can be overridden in the derived class. Now, how we do this? With a specific keyword that is override. So this is another keyword from the language. So this is something you cannot use. So these are keywords, right? And then base class, in this case, rectangle, can force all derived class to override a function by making it pure virtual. So when you declare the function on the base class and then you delete it, so you basically use equals to 0 means delete this function, then at compile time, you're forcing all the derived types to implement this function. And this is called pure virtual function, and it has some meaning. One warning is not confuse function overloading with overriding. So remember when we did overloading a few lectures ago, we were basically picking from all functions with the same name but different parameters. For example, the sum function, you can sum 2 integers, 2 floating points, 3, I don't know, bytes, whatever, and you can have the same name but with different parameters. And then you overload this function. And then depending on how you call this add operation, at compile time, the compiler will say, okay, you are calling this function from all these possible functions, right? And if you do this, the functions don't have to be in a class, so they're just functions. So overriding, it's quite similar the word, but it's completely different the meaning. So you would pick from functions with the same arguments and names in different classes of one class hierarchy, right? So if you override the function, depending on which object you are using, you will pick this function, and this is something that will happen at runtime. So it's dynamically solved. There's this notion of abstract classes and interfaces. So this is basically a name to some specific classes. This is not a keyword of the language, it's basically an idea on object-oriented design. An abstract class, let me close this because something is weird with the presentation. See, the margins were wrong. Okay, now it's better. Sorry. An abstract class has at least one pure virtual function. What is pure virtual function? Again, it's just a name for a given syntax. So if we go back, this is pure virtual function. It's going to be whenever you mark a function from a class as virtual and then you delete it. And then an interface will be a class that has only pure virtual functions and no data members. So that's a name for a given class. So it's not something that is on the language or something that you need to define. So if you see a class that has all its members with pure virtual function and not data members, then you call this, oh, this is an interface. But it's the same. So the compiler doesn't care about these names. It's a way of modeling how virtual works. So a class with virtual functions has a virtual table. I'm going to go quickly over this because it's a bit boring. And then whenever you call a function, the class will check which of the virtual functions match the signature that matches this signature should be called. If you have like a overriding function within the class, you say, okay, you have a square and you're calling this function, then you need this from the virtual table. This is what it's called runtime polymorphism, and this costs sometimes, but it's very convenient, right? And the idea behind interfaces, so remember, this is just a name. When we have a class with all its function members equals to 0, this means deleted. We call this interface. So the idea is you must enforce our classes to implement some functionality, and we will see some examples with the patterns. So if you use an interface, whenever you derive from the interface, the compiler will force you to implement those functions. So if you derive from an interface and then you don't provide an implementations for the deleted functions, then you will get a compilation error. This allows thinking about classes in terms of abstract functionality and also hide implementation from the caller. So this is a common way to provide a sort of API. And this allows to easily extend functionality by simply adding a new class. Here's one example, right? So let's go quickly through it. Again, try it. So we have a class that is printable, struct and class is the same, you know this. And then we will define one unique virtual function that is called print, and then we will equal this to 0. This means we delete it. We are making this member function pure virtual. This means that whenever we derive from this class, we need to provide an implementation. So let's go, for example, another type A, whatever, will publicly inherit from printable. So we need to define the same print function and then override it. So we need to specify this print function is actually overriding this guy that you are forcing me to implement. And then in this case, I just print the name of the class. I can do the same with B, right? And then you can print A or B, and then you will get the output on the console. So this is like a really dummy example. One example of inheritance in our field, as usual, I like to go to Open3D because it's a good code base, so you can use it as example. And in this case, for example, they define a new type that is called geometry 2D. So this is an interface in terms of there's no real data members inside, and all the functions are marked as virtual, pure virtual. So they're all deleted, right? And then you are forced to implement this functionality within whenever you derive. So this is a way to say, okay, all these 2D geometry types needs to conform to this particular interface. So for example, of a given image, you need to override all these methods. Actually, these two methods are not marked as virtual, this one and this one. So it's actually not an interface, it's an abstract class. So, but in this case, you also override it. For the sake of the example, it's the same. So you have override here, override here, here, and here. So you're basically providing a full specification for this particular derived class. And then of course you will have different meanings for different type of geometries. So whenever you want to see if a image is empty, you can, for example, do, okay, if the rows and the columns are not 0, then it's not empty. But for other 2D geometry, like a range image, for example, then this might be different. It all depends on your type. So this is like an example of how we use it in our field. Then there's another concept that is based, is the part of the basic of object-oriented design, that is called polymorphism, right? This word, it's just a fancy word that came from the Greek language. That apparently, this I have no idea, polis means many or much, and morphe means the shape. So it's many shapes. So the idea behind polymorphism is that you can have different objects that can behave differently and take any sort of shape. So I have one question, I guess, for this example. Sorry, there's a bit of delay. So how would this example be different if it was an interface? So the only difference is that if, for example, you don't provide, so let's say that you don't provide an implementation for this. So in this case, if you don't provide an implementation for these two functions, then at compile time, you will not have any error, right? Unless you want to call it. But you're not forced to do this for these two particular functions because they are not virtual. But for these other functions, you're forced because of the virtual. So you're forcing whoever inherited from geometry 2D to override this function. Why? Maybe because for some reason you want, in some part of the library, for example, you always want to have access to these two methods, right? The get min bound and get max. You always need this, so you say, okay, everyone guys, just please implement this function. Even if you don't care, just do it because I will need to use it for, I know, writing the images or the geometry to this to the file system. If we want to make this an interface, then we should mark this as virtual, and then now we will be forced to implement also these two functions here, right? And if you don't do it, you will get a compilation error. That's the only difference. It's like how you guarantee at compile time that someone will implement a given function. And we will see like some examples of this in a few minutes. So polymorphism, going back, allows morphing derived classes into the base class type, right? This sounds weird, but sometimes it's very convenient. So for example, we have a base class that in this case could be geometry 2D, and then we have the derived class that this is the image 2D. We can make this image behave as a geometry 2D object, right? So we are having many forms of the object because the object can be a geometry 2D and also an image. Of course, you cannot do this with, I know, fruits and images because there's no real relationship between these two objects. Let's start with a simple example, and then again we have this class rectangle with the same two data members. And for example, we have a class square that we already saw this. We just override the constructor and then use one only parameter, right? So there's no real polymorphism on this example because if you want to use these two types, then you have a square and a rectangle. And every time you need to, for example, print the width of the rectangle and the height, you need to use each specific object and call its member function. So you're not really morphing any object into another one. So this is objects, they could be related or not. Then there's another example. You say, okay, I want to improve my code, how I can do this better. Then you say, okay, on the class rectangle, I will define a new member function, not virtual, a normal one, just a function within the class. And then I will print this guy, right? And then on this case, I will also define a member function, and then I will provide a different implementation. Yeah, so far, nothing new. So this is better than manually calling the getter methods like we did on example number 1, but this still needs to explicitly call the print function. So how you can check that you're not doing polymorphism, because when you need to print this, then you have a square here and a rectangle here. So again, we have one object of each class and we are using it independently. So nothing like new or fancy. But then we can start using virtual and try to make this, like implement this idea of polymorphism. So the rectangle will have a class that is print that will be marked as virtual, right? So this means that any derived type can implement and override this particular function. If we go back to example number 2, so in this case, this is not function overriding, but function overloading. So this is basically two different functions that are not related to each other. So there is no relationship within the class hierarchy for these two functions. And then we mark this as virtual, and then on the square, we override this function. And now there is a relationship. We are saying, remember the print function you have on your base class? Then I take responsibility for this implementation and then override the base implementation. And then, for example, we can have a print shape function, like this is outside the classes, it's a normal function that take as input argument rectangle. Why rectangle? Because this is the base class. This could be also be geometry 2D. A square is a rectangle, so it can be morphed into a rectangle and act as a rectangle because it is a rectangle. A square is a rectangle, but a rectangle is not a square. That's the relationship. So you can actually pass a reference to a rectangle, no matter if you have a rectangle or a square, and then you just call the print function. And then this is example, so you have a square and a rectangle, and then now you're using polymorphism because you're just printing shapes, and it's quite abstract. Just print shape. I know. These are the objects, just print it. And then you need to really care, like if this is a rectangle or a particular square. So if you go through, I recommend you to implement these 3 examples on your computer, and you will see like the difference while coding, right? So congratulations, now we are using runtime polymorphism. We are printing shapes to the standard output, deciding at runtime which type of shape it is. So what happened at runtime is that whenever you call the print shape, for example, square is a rectangle, so you call this, and then you say, okay, this object is a square or a rectangle. I mean, this is not an if else, right? But think it as this for now. And then, okay, it's a square, so whenever you call the print function, use this one, right? If you don't use virtual or override here, then there's no relationship between these two functions, and then this you cannot do. Another step, if you want to try it, but for this you will need to use pointers that we will see on next lecture, is you say, okay, I want to have a vector of shapes, and I just want to iterate through this vector and print it. If you copy this example on your computer, you will see that this works. And again, so let's hide the weird part for now. So okay, so we have a rectangle, so I will just hide the pointer types, and basically we have a vector of rectangles and we call this shape, and then we will put, actually I need them placed back, so let's hide this and then make unique, just hide this, and now this is the syntax you're used to. And then you will place back into this vector 2 shapes, one rectangle and one square. And this is quite generic. You don't care like if it is a rectangle or a square. The only thing you need to care is that they all conform to the rectangle or the base class, right? Because that's the vector that you have. And then you can, later on, you can iterate through all these shapes and then just say shape print. And then you will be calling at runtime, you will be picking which function from the virtual table, if it's a rectangle or square, which one it is, and then you will call this one. This is really convenient. And if you inspect the code, it's quite abstract, right? And then you might wonder, when is this useful? Basically, when you need to encapsulate the implementation inside a class, only asking to conform to a common interface. So you can have a particular interface, and then you can you actually want to hide for some reason the implementation of this, and say, okay, this is the interface, this is the API of the classes, like this is the geometry to the classes, they all do these methods. You can all clear these geometries, you can get the bounding box for this geometry, whatever. Don't look to the implementation, that's my problem, just stick to the interface. It's often used also for working with children of some base classes in a unified manner. So if you go back, so shape print, you basically are using calling members from the base class and children classes or derived classes and an unified manner. So you use the same syntax, and this usually avoids the mess that a C programmer will do. Like, if this type is this type, then do this. If not, do this. And maybe you can do this. It's a mess. You have an unified manner of working with different types. This also allows you to enforce an interface in multiple classes, like forcing them to implement some functionality. That's basically the pure virtual functions. And there's something that is called strategy pattern that you will probably be implementing on homework 8, and where some complex functionality is outsourced into separate classes and it's passed to the object in a modular fashion. So some thoughts on class hierarchy. Difficult word. Sometimes classes must from a hierarchy, and the idea is that you should distinguish when you design your code between is a and has a. So remember to like these two phrases. So whenever if a square is a rectangle, then you need to the right? But there's another idea that is has, that is called composition. But for example, a square is a shape, so a square can inherit from shape. Student is a human, so can inherit from human. For example, car has a wheel, so there is a composition. So let's say you have a type wheel, and then the car does not inherit from a wheel because it's not a wheel. It has a wheel, so you should not inherit from each other. You just need to, inside the car class, you will have one data member that is going to be one wheel, or a vector of wheel, or whatever, right? The idea is that Google also recommends to prefer composition, and then my recommendation is don't get too excited with this object-oriented design. So particularly in our field, we don't need to do like really abstract modeling with source code. So if you, you can go to, so if you start like going deep into the class hierarchy, then you can go infinite, right? Because an image can be a geometry 2D, but the geometry 2D can be a geometry, and then the geometry could be a math space, and then you can go like infinite amount of levels in the class hierarchy, and then it's get really complicated. It's going to be slow. And then if you need to actually inspect the code, it's impossible. So if you need to see something from the base class and then you are inheriting from 50,000 classes, then it's impossible. Then you need to click, go over all these source code files until you get to the base class. So don't get too excited with, oh, I have a wheel. A wheel is also a shape, and just don't get too excited. Whenever you feel like this will improve the code performance and readability, use it. But just be careful. Okay, so the last thing about object-oriented design in C++ that we will discuss before diving into patterns is something that is called typecasting. So now we can create our own types, and we can also express relationships between these types. So we can do inheritance, for example, and then we can also do composition. So we can put an object inside another class member in the code. And then we have all these new types. So one natural question will be how to convert from one type to another. So this is called typecasting. So every variable in a C++ program has a type, and then the types can be converted from one to another. Not always, but usually. So type conversion is called typecasting, and there are 5 ways to typecast in C++. The first one is static cast. This is the most widely used. Then there is also reinterpreter cast. You should be using this, or might be using this, for homework number 5. There is also const cast and dynamic cast, right? And lastly, the fifth one, is a C style cast. This, the C++ programmer, we also call unsafe cast. Why is this? By the way, after this lecture, you're not allowed to use this C style cast, and this is the reason why. If you do this like between parentheses cast, so you have a variable, you will see the syntax and you say this is float, then the compiler will first try to do a const cast, then a static cast, and then if this fails, it will do a static cast and then a const cast, like after the static cast, then a reinterpreter cast or a reinterpreter cast, and then a const cast. Why is this unsafe? Because whenever you use this C style cast, then you have no idea what is going on. So it could be any of these 5 possibilities and you don't get to pick which one you use, right? Now I'm going to be fast with this. So there are only 2 probably casting type methods that I care. Is static cast. You know, whatever is static, it happens at compile time. So whenever you say static cast to a new type this variable, it's something that it should happen at compile time. So it's not something that it will happen at runtime. Whenever you compile the program, this will happen. So you will, with this, you can convert type of a variable at compile time. It's rarely needed to be used explicitly because this can happen implicitly for some types, but it's never a bad idea to use it. And for example, for classes, you can pointer to an object of a derived class can upcast to a pointer of base class. So for example, you can do static cast a rectangle and then you cast a square, right? The full specification, it's complex, but this is probably the one you might be using. Dynamic cast is something that it will happen at runtime. So it's something that while the program is running will happen. So you will need to use pointer for this, and it's used to convert a pointer to a variable of the right type to a pointer of a base type. So the idea is that you should be avoiding to use dynamic cast because this is cost. So this costs time at runtime, and unless it's necessary, it's very likely that you can express these ideas in a better way. But in case you need it at runtime, you can change the types of your classes only when they are related, right? When you have, for example, a base class and a derived class. This one is the one we saw 2 lectures ago. So you just reinterpret the bytes of a given variable from another to another type, and this is extremely unsafe because the compiler say, okay, you know what you're doing. If you have 8 bytes and you say this is a floating point, it's up to you. So this is really a low-level cast that is, you should only use this whenever you write binary files. And then the const cast is basically to add or deconstify any object. Some comments on this, and then I will skip it. You can watch it later on or read it. So that was basically it. So that's all I care for you to know about object-oriented design. Like, you should know roughly what is inheritance, how to inherit from one class. You also would like to have this idea of polymorphism, and also like how to define virtual function and override those functions on the right class. But that's basically, it's not all of object-oriented design, but it's what I care. So we will see 3 patterns right now. Depending on the time, I will go fast or not. So let's start with something that is called strategy pattern. So if a given class, so the idea of this pattern is that I want to show you that these ideas from object-oriented design, you can also use it for nice patterns that are not necessary. Oh, I have a vehicle that is a object in the world. So this idea of modeling everything with inheritance is good up to some point. But you can also use the underneath infrastructure to create new patterns that are not strictly related to these objects and classes and whatever, right? So the strategy pattern is, the idea is that if a class relies on complex external functionality, you can use this pattern, and this adds or switch functionality of the class without changing its implementation. That's why it's called strategy. So you have a class, and then you want to write different strategies for this class, for a given thing. All strategies must conform to one interface, and this is one example. So we have a class strategy that is pure virtual function is only one. So we have only one pure virtual function. This makes this class interface, right? And then we can have 2 strategies that are different, that will inherit from this strategy, but not in the sense of like, oh, strategy A is a strategy, but in the sense of, okay, I need to implement a new strategy and I want to conform to this API. I need to override this print function, right? So far, nothing is new with this source code. We just define an interface that is a strategy and derive two classes from this interface, implementing the virtual methods. The strategy pattern comes into this place. So we have another class that is the source, like the sync, class of this strategy pattern. And then we will use composition and we will store a reference to the strategy, right? So if you see here, we are not storing a reference to strategy A or B, just strategy, right? And then we will provide a function that is print that will basically call the print method from the strategy. And then this class holds a const reference to the object, so it cannot change it. And then the strategy will be picked when we create the object of my class. So you can create a new object of this class and say, okay, I want you this strategy. And then you use A or B. And because C++ supports polymorphism, this strategy A can form a strategy, not A or B, just the base class that is this interface. And we don't need to hold a reference to all types of available strategies. So how you can see that someone does not know how to use the C++ language, because with this type of patterns, you will inspect the code and then you will have if blah blah blah, then create this strategy A. If blah 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 else, then this variable do strategy underscore B, and then you have like multiple objects within the class that you pick like with some ID if and else at runtime. And there's much better way of doing this with this type of patterns. So you have one strategy, you have that is the base one, and then you have as many other strategies as you want. And then you stop there with the hierarchy, with inheritance. And then whenever you want to use, okay, I want to use this particular strategy, then you create this my class type with this given strategy. And then you don't need to do if, else, whatever. This is much better, right? It's better to read also. And then the print method has nothing to do with the one that we define. So this print here, so don't be confused, this could be called bananas. I like bananas. It has nothing to do with this guy, right? Try this example. So for example, this is how we will use it. So we create strategy A and B, and then we will have object 1 and 2. So it's all fake names, and then we pick which strategy to use, like passing the strategy to the constructor, right? And then whenever we call print, so we can do this in a loop, we will pick different strategies, right? So the idea is that you should not overuse it. So this is, so all the patterns are usually nice, but again, you should not get really, really excited. So just use it whenever it improves code performance or readability. If your class should have a single method for some functionality, and then we never need to another implementation, then don't make it virtual, and then use it mostly to avoid copying code and to make classes smaller, right? I won't go over to it, but on the files that I provided to you, there is this there's one example of one research project I did some time ago. So hopefully this works now. So don't even try to compile this code because it doesn't work. So this is like 5% of a big project. So but I just cherry pick the files to give you an idea of when you can use this. So in my case, I was doing ICP for point clouds, and then I had different implementation for this ICP. And then for now, let's disable. It's already disabled. Great. And then, in order to pick these different strategies, I have this ICP strategy that is basically an abstract class that has an interface that all the derived types that will be the different strategies needs to conform to this particular interface. So besides details, so we have one function that is called process first cloud. So you need to provide an implementation if you want to be a strategy for ICP, register new cloud, the name of the strategy, and so on. So you can inspect this. So it's a big class, so don't worry. And then here I picked like 3 of the strategies I was using. And in this case, if you see this one, for example, so there is this DLOAN thing, and it inherited from this strategy. So I am now providing a full specification for this particular strategy for ICP. And then we need to provide an implementation for process first clause, register new clause, and so on. How? With the override keyword. So all these override functions are overriding the ICP strategy functions. If you don't do it, then you will get a compilation error. Don't even try to compile this because you're missing most of the files. And then here you can also see like the actual implementation of these things. And there's another NARF ICP using NARF key points. Again, the same interface with different implementation. And then, for example, I was using ROS for this example. And then you can pick, like, with this registration node that I think I also give you the implementation, which strategy you want to use. And actually with this, you can also change this functionality at runtime. It doesn't make much sense, but you could do it. And here on the node, you can see that basically you're holding a reference to this ICP strategy. So this is an example if you really want to see how you could also use it for ICP, for example. Then Singleton pattern. Just be careful with this because it's quite easy to understand, I guess. And then if you start to use it everywhere, then it's not a good idea to overuse this pattern. So it's easy to use and also easy to misuse. So be careful. So second pattern that we can use. Let's pretend that we want only one instance of a given class for any reason. Have one class, for example, the bag of Vizzo word dictionary you might want to use for your final project, and then you want one object of this class. You don't want people to create multiple objects. For example, this for a rectangle doesn't make sense because you probably want a bunch of rectangles in your program for any reason. But for the dictionary in your program, there's only one unique dictionary, and then you don't want anyone to copy this or create new ones. Then you will use the Singleton pattern. Without C++, this will be an if-else, right? You will see, okay, if objects are created, then don't do it. It will be a mess, right? But we have the compiler, and then we can use it in our favor, right? And then we can make sure that nobody creates more than one instance of a given class at compile time, right? And do not overuse it. It's easy to learn, but usually hides a design error in your code. Sometimes this is still necessary, and makes your code better, but just be careful. One disclaimer: this Singleton pattern does not use any idea of object-oriented design, but it's part of the patterns I want to teach you, so that's why it fits into this lecture. By the way, you need to use this for homework number 7, so pay attention. How we can do this? So we can delete any class member function, as we saw it with whenever you, for example, you have these virtual methods and then you equals to 0, then you delete this function. We also saw it on previous lecture. This also holds true for special functions like the constructor, the copy constructor, the copy assignment operator, the move constructor, the move assignment operator, and the destructor. The special function also holds true. You can delete these functions. And then just remember that any private member, this function or data member, can only be accessed by a member of the class. So someone outside the class cannot access this this member, and also if you inherit, you could not access this member as well, neither. So how we implement this Singleton pattern? We want one unique class across the program. So first of all, let's hide the default constructor and the destructor. With this, we say, okay, actually, yeah, so here, I didn't forget it. So we are saying we have one Singleton class, let's call it, and you have the default constructor and the default destructor, right? So you don't provide a specific implementation, but you make this private. With this, you are forbidding anyone to create a Singleton object. So for now, you just hide the constructor. This, if you want to create an object, you will have a compilation error, right? This completely disables the possibility to create a singleton object or to destroy it. So good. First of all, we are going good. And then let's delete all copy capabilities. So no one can copy objects of this class. So for this, we need to attack the copy constructor and the copy assignment operator. How we do this? We just delete this function. This is the same of doing equals to 0. Basically here you have the copy constructor and then the copy assignment operator. You should just say delete. So if anyone wants to call these special functions, compilation error. It's not allowed, right? And then you will start hating the compiler. But believe me, it's your friend. This completely disables the possibility to copy any existing singleton object. We done? Not really. So now we cannot create objects of the singleton class. We cannot copy objects. How do we create the unique instance in my program? Because it's not allowed anymore. So how? Compiler to the rescue. As usual, C++ has a powerful compiler, we should use it. We can create one unique instance of the class, and probably you might be guessing that this should happen at compile time. I will do this with static, right? So we will provide one member function that is static, and with this we are allowing to access this function outside objects of the class. So if you go back to the static explanation from previous lecture, you can just call singleton ::, and then this function. We will call this function getInstance, so this is the name you pick it, this is quite common, and we will return a reference to a singleton object, right? And the key idea here is that, let's pick this color, you are creating an instance of this class at compile time, and it's static. This means that when you compile the program, this object will be created and will be part of the data of your program. And that's the unique object you create from the class, right? And because you disable the copy capabilities and constructing and destructing, this object will be alive across the whole duration of your program, and you cannot touch it. You cannot delete it, you cannot copy it, nothing. It's one unique instance, so it's quite nice, let's say. So this is the full pattern. There are much other better ways to implement this pattern, but I will say this is the most easy singleton pattern in C++. How we will use it? So we provide this on a header file, for example, and then, so let's throw this on singleton.hpp, and then we cannot create objects, but we can call this getInstant function, right? With this syntax, because it's a static member function of the singleton class. And then we just get the reference to that object inside this class that was created at compile time. So we are referencing something that is already alive, right? And then, for example, if you forget about the fact that you're using a singleton, then this will provide this will give you a compilation error, because in this case you're calling the constructor and it's private and you are not in, so this main is not part of the scope of the class, so you cannot call it, right? If you want to copy this, so basically you are calling the copy constructor here, another compilation error, you are not allowed to do this. And then if you want to do the copy assignment operator, again you cannot do this, you will get a compilation error. And here I have like a small example for you. Singleton pattern. So basically the only difference with the slide is that I added this private member that is just an integer, and then here I provided a set and a getter method, so you can actually access the data members inside the singleton class, but through this getInstance function. And in this case you create this reference to the instance, and then, for example, you call foo, and first it will have 0 because that's the initialization value, and then you will set foo to 50, and then you print it, right? So you have one instance across all the program, and then you can use it everywhere. So why this might be complicated? Because everyone who has access to this interface will have access to the same object So on a multi-threading scenario, this will be a mess because you can have multiple threads of your program accessing the same object in memory. So this is one of the reasons you should not overuse singleton pattern. But for now, let's say that for the dictionary for your final project, you want only one dictionary, and then that's it. And then you want to guarantee that no one else create dictionaries, right? So that's the singleton pattern. No real inheritance, so no object-oriented design, just another pattern. There's a funny pattern that is CRTP, that is curiously recursive template pattern. So this is another pattern that you can use. But this involves inheritance. Again, it's not a matter of like if this object is a whatever, it's a matter of using the underlying infrastructure to provide better patterns. And then for some reason, let's pretend that you want to create new types. But every time you create an object of your new types, for some reason you want to print to the standard output the name of the type. How C people will do it, or how C++ people without knowing patterns will do it, you just implement a bunch of functions like we did on the first examples. So if you see the print examples, they are similar to this. And then you say, okay, for this example, then print this, and then you type all the types. You basically like copy paste code. There's no compilation guarantee for this, and there is a much better way of doing this. So you will first define a base class that is called printable. So this is what I am calling basically, and then this will be not really a class, but a class template. We will see templates soon, but you already have some idea, I expect, right? So this class printable, we have a public constructor, and then it will be explicit because it's not the default one, so it's something that we provide. And then whenever you create any object of this printable class, then you will print to the standard output the type. I will do this with boost core demangle. So this is part of the boost libraries. You just call this function, you get the name of the type at compilation time. That's basically. And then the R here of the recursive pattern is that you can actually use this and say, okay, I have one type that is called example1, and this could be any name that will be inherited from printable, that is this class member, and the type will be example1, right? So here's the recursion of the template. So it's a recursive thing, right? And with this, you're saying, okay, I want to inherit from this type publicly, and because I don't provide any other implementation, I will be always calling the constructor from my base class. So whenever I create an object of example1, I will get into the standard output the name of the type, and then the same for other types, right? And then if you use this, if you try this at home, you will see that if you create object of these particular types, then whenever you create the object, you will get this print message on the standard output. So you will have like type created, whatever. So this is something that you might find useful to use at some point. So a summary, we're reaching the end of the lecture. So we saw some small ideas on inheritance and polymorphism. So these are basically the pillars behind object-oriented design. Again, I don't expect you to create a class hierarchy for like the world and the humanity. Just use it whenever it's convenient, like for example, forcing the right types to conform to a particular interface. Also, we saw briefly typecasting, so whenever you need to convert from one type to another, and we saw 3 patterns. So the singleton pattern is something you need to use for homework number 7. Strategy pattern will be most likely used on homework 8, and then the CRTP might be used or not. But the idea is that you see this pattern on how to use the language to create your own tools to work with. There are 2 videos for this week, like 10 minutes videos about the pillars of object-oriented design, so encapsulation, abstractions, inheritance, and polymorphism. And there's also one specific video for polymorphism. And then you need to watch this video. So next, this is something that it's for people who don't have experience with C, it's probably going to be challenging. So next week we are going to dive deeply into memory management with C++, and for this it's a prerequisite to know pointers. So Igor already, the one who teaches this class before me, he already did a good lecture on memory, on raw pointers and memory management with C, but using C++. So this lecture is a prerequisite for next week lecture, right? So you should watch this. It's about 1 hour. You should try the examples Igor does there and try to get some understanding on this, because otherwise next lecture will be quite difficult for you. And I know pointers is not an easy topic, and actually it takes some time to get used unless you have an electronics background engineer or electrical engineer, or you already have experience with C. So if this is not your case, then you should probably start looking into it. Just watch videos on YouTube, just get information into your brain, so your brain start adapting to this idea of pointers, right? There's some reference as usual on CPP reference about object-oriented design, so how to derive classes, what virtual means, override, whatever, and then all the typecasting we covered, the references are there. You just can click and see more information. And there's also like some links about the 3 patterns we saw on this class: the strategy pattern, the Singleton pattern, and so on. And then that's basically it from my side. If you have any questions, this is the moment to ask. Otherwise, you can do it on Friday or on the Discord channel.